Where we are now, on the west coast of northern Norway, the sun hardly ever sets in the summer. This is because we're very close to the Arctic Circle, which is only a few hundred kilometers north of here. However, the Arctic Circle is a moving target. This is because the Earth's orbit around the sun changes slightly through time. This means that the amount of sunlight we receive where we now are will change from year to year. This is the same at any other point on the Earth. During this lecture, we'll learn about the natural drivers of climate change, also called the natural radiative forcing of climate. In particular, we'll learn about the sun and how it has affected climate over the Earth's recent past. If you live at high latitudes of either the northern or the southern hemispheres, you will have experienced the midnight sun. In the northern hemisphere, the latitude where the sun remains continuously above the horizon for 24 hours is called the Arctic Circle. It is located at 66.6 degrees north of the equator. The equivalent is found south of the equator at the same latitude in the southern hemisphere, and it's called the Antarctic Circle. At latitude 66.6 north or south of the equator, the number of days experiencing the midnight sun increases. For example, at the Arctic Circle, the sun is barely above the horizon at midnight. However, as you go north, the number of days with midnight sun increases. At the North Pole, you will experience 186 days, or half the year, with midnight sun. Similarly, at the North Pole during the winter, you will not see the sun for 186 days of the year. Now you might be asking yourself, what does the midnight sun have to do with changes in climate? As long as the number of days with midnight sun remains the same from year to year, there is no effect on climate. However, on long time scales, the position of the Arctic Circle and the Antarctic Circle will migrate north-south. This migration of the Antarctic and Arctic circles is controlled by the angle of the Earth's spin axis. On long time scales, the angle of the Earth's axis can change several degrees. This change will cause a change in the location of the Arctic and Antarctic circles, as well as the amount of energy received from the sun at a given latitude. As we speak, the Arctic Circle is moving northward with a speed of 15 meters per year. This means that the regions of the globe experiencing the midnight sun are decreasing. The angle of the Earth's spin axis relative to the plane of the Earth's orbit is referred to as the obliquity. The obliquity of the Earth is currently 23.4 degrees. However, it oscillates between 22.1 and 24.5 degrees, and a complete obliquity oscillation of 2.4 degrees takes approximately 41,000 years. Currently, obliquity is decreasing and the Arctic Circle is moving northwards. As a consequence, the summers, such as the one up here in the north, are going to get colder and colder. As the summers in the high latitudes get colder, the winters in the mid latitudes are going to get warmer. This is because the amount of radiation received south of the Arctic Circle is going to be increasing. These effects will be mirrored in the southern hemisphere, where the Antarctic Circle is moving southwards. As changes in solar radiation due to obliquity are stronger in summer than in winter, particularly at high latitudes, there is also a significant change in the annual mean solar radiation. This change in annual mean solar radiation is not the same at all latitudes. At high latitudes, decreasing obliquity decreases annual mean solar radiation, whereas at low latitudes, decreasing obliquity increases annual mean solar radiation. So, what is the consequence of changes in obliquity? As postulated by the Serbian geophysicist and astronomer Milutin Milankovic during the 1940s, if snow and ice at high latitudes can persist through the summer from year to year, you will ultimately have an ice age. As shown in the previous figures, cold summers require low obliquity. This effect is enhanced at high latitudes where changes in obliquity are likely to have a strong impact on changes to snow and ice. To complicate things, the Earth's spin axis experiences a slow wobble or precession through time. As a consequence, the spin axis will not always point in the same direction with respect to the fixed stars. Due to the Earth's orbit being an ellipse and not a perfect circle, the direction of the spin axis also has a consequence for the amount of radiation received at the Earth's surface. The amount of radiation received by the Earth at the point of its orbit closest to the Sun, the perihelion, is significantly larger than what it is received at the point on its orbit farthest from the Sun, which is called the aphelion. As a consequence, if Northern Hemisphere summer occurs during aphelion, the northern latitudes will experience relatively mild summers. Similarly, the winters at the same latitudes will be relatively warm. Due to the precession of the Earth's spin axis relative to the fixed stars, the location of the seasons will shift relative to the perihelion and aphelion with time. This is called the precession of the equinoxes. The time taken for a full cycle is approximately 21,000 years. What is the consequence of the precession of the equinoxes? In the annual mean at the given latitude, there is no net change in solar radiation. This is because the warm summer of one year is compensated by a correspondingly cold winter. This is unlike the response to obliquity. However, much of the climate system responds non-linearly to changes in incoming solar radiation. For example, snow and ice will respond differently to changes in summer and winter solar radiation. In particular, summer radiation at high latitudes has been found to be important for the growth and the decay of large land-based ice sheets. In this case, the precession of the equinoxes plays a crucial role. To summarize, the combination of obliquity and precession of the equinoxes is key to changes in climate on millennial timescales. On millennial timescales, changes to the Earth's orbit and the spin axis dominate changes in climate. However, on shorter timescales, the luminosity or brightness of the Sun changes. This is due to varying sunspot activity. Sunspots are dark spots on the Sun's surface surrounded by brighter, hotter areas. These hot areas increase the luminosity of the Sun, thereby increasing the solar radiation received on Earth during periods with abundant sunspots. Sunspot activity has been found to vary regularly with a cycle of 11 years. However, during the last half of the 17th century, there was a prolonged period with hardly any sunspots. This period is called the Maunder Minimum. The Maunder Minimum overlaps with the Little Ice Age, and during this period, Europe and North America experienced extremely cold winters. Here in Norway, the glaciers expanded and the Viking colonies on Greenland were abandoned. In addition to external forcing of climate by changes in the amount of solar radiation received on Earth, there are important internal factors impacting climate, such as volcanoes. Explosive volcanic eruptions can eject large amounts of dust and aerosols into the stratosphere. Once in the stratosphere, which is more than 20 kilometers above the Earth's surface, the dust and particles and aerosols can remain for many months and have a significant impact on climate. Volcanic aerosols consist of sulfate, which when reaching the stratosphere acts as an efficient reflector of incoming solar radiation. One of the largest documented eruptions was that of Tambora in Indonesia in 1815. This eruption was massive. The volcano ejected ash and aerosols to a height of 50 kilometers, which spread around the globe within a few months. The stratospheric aerosols reduced the amount of incoming radiation for nearly 2 years following the eruption, and the year 1816 was known as the year without a summer. As shown here, the combination of volcanism and sunspot activity has had a significant impact on climate over the past millennia. 1,000 years ago, during the peak of the medieval warm period, when the Vikings were prosperous and settled Greenland, climate was warm due to the combination of high sunspot activity and low volcanic activity. The medieval warm period was followed by a prolonged period with little sunspot activity and a significant number of volcanic eruptions. The combination of these two factors is thought to have caused what's called the Little Ice Age. In Europe and America, the coldest temperatures with much hardship were recorded during the 17th century. To summarize, on short timescales, sunspot activity and volcanism is a dominant natural forcing of climate. However, on timescales longer than millennia, changes to the Earth's orbit around the Sun is important. This cyclic change in radiation received on the surface of the Earth has caused large changes in climate of the past. In particular, it is responsible for the periodically reoccurring ice ages.
Here on the west coast of Norway, the summer is still warm and there's no sign of an advancing ice age. As we learned in this lecture, the sum of the drivers of climate should be moving us gradually towards a colder climate. So what's happened? Why isn't the system responding to the natural forcing of climate as we expect? This will be the topic of the next lecture.